In this lecture, we are going to complete our discussion of molecular orbital theory of H2 plus dihydrogen cation. So far, we have written down the Hamiltonian, and the reason why we are working with H2 plus, as we have said several times already, is that it is a unique case of a 1 electron molecule. So here we have minus h cross square by 2me del E square, that is the kinetic energy term of this lone electron, minus q E square by Ra minus q E square by Rb. These are the potential energy terms for the attraction of this electron by the two nuclei, and q E square by capital R, where capital R is the internuclear separation, is the term in the Hamiltonian operator for internuclear repulsion. So we have formulated Schrodinger equation this way, and we have said that we are going to construct the molecular orbital not by solving Schrodinger equation directly, even though it is possible. We are going to construct it by a rather unique technique by taking a linear combination of atomic orbitals. And when we do that, this is where we are. We made a little bit of progress, identified a something called an overlap integral 1SA 1SB over all space, and we have got two wave functions. Psi 1, this is the bonding orbital 1 by root over 2 plus 2s multiplied by 1SA plus 1SB, and psi 2 1 by root over 2 minus 2s 1SA minus 1SB. We have plotted the electron distribution. These are the contour diagrams, and these are the profiles that you take through these two, and from these we have said that it is quite obvious that in this case, in the upper case, that is where you have a build up of electron density between the two nuclei, that is going to lead to stabilization, and here you have a depletion of electron density. If you take square of this between A and B, that is going to increase, that is going to contribute to increased internuclear repulsion. So this will be a higher energetic state. So this here is called bonding situation, bonding lowers energy, and this here is called anti-bonding situation, anti-bonding orbital. Why? Because there is an increase in energy compared to isolated atoms. If there was no change in energy, we would have called it non-bonding orbital, right. So let me write the expression like this: E1 is equal to integral psi 1 h psi 1 over all space. So if we expand this, and again the way to do this is, once I write this, please stop the video, do the expansion yourself, it is elementary, and then when you reach a point where you get some strange looking quantities, then you should turn the video back on. Okay. So this is what we have. We have replaced psi 1 by 1 by root over 2 plus 2s multiplied by 1SA plus 1SB in the bra vector as well as the ket vector. Of course, I can take the constants out and I will get 1 by 2 plus 2s outside. So that is sorted. Inside we have this wave function h hat, wave function integrated over all space. Expand it, you are going to get 4 terms: integral phi 1 SA h hat phi 1 SA plus phi 1 SB h hat phi 1 SB plus phi 1 SA h hat phi 1 SB plus phi 1 SB h hat phi 1 SA. And now we have to expand these terms and write them in some way that we can understand. Similarly, we can write an expression for E2. The only difference between E1 and E2 is that for the last two terms in E2 the signs are negative, whereas the signs are positive for all terms for E1. That is the only difference, terms are actually all the same. Alright, so let us try to evaluate this one by one slowly. This is where we are right now. We have got the wave function, we have got an expression for the expectation values of energy for bonding as well as anti-bonding situation. Let us work with the energy of the bonding orbital and let us try to expand this a little bit. While doing that, since we do not know what these integrals are, we are going to define them, we are going to give them some name. That is the best we can do at the moment, because see as I said, 1SA is not really eigenfunction of h hat. So you cannot just write E0 and bring it out, that is not going to work. So what we say is whenever we have the same orbital before and after in the bra vector and ket vector, we call that integral HII or HJJ, both are actually the same. It does not matter because both are 1s orbitals. When we have say 1sa in the bra vector and 1sb in the ket vector or the other way around, we call it Hij. Now Hij is equal to Hji, that comes from the property of Hermitian operators. There is something called turnover rule, where if you have something like integral phi 1 h phi 2, you might as well write integral phi 2 h phi 1, does not matter, it is all the same. For this course we are going to take it axiomatically. And the last thing that we know already is the overlap integral, that in any case is very easy to understand. So we are going to write the expression for energy in terms of these integrals now. What is the first one? Integral phi 1 sa h hat phi 1 sa, that is HAA, right, or H11 or HII, whatever we want to call it. What about the second one? That is also going to be HII, because we have the same 1sb in the bra vector and ket vector. The last two terms are going to be Hij or H12 or HAB, whatever we want to call it, because there we have, if we have A in the bra vector, we have B in the ket vector, if we have B in the bra vector, we have A in the ket vector. So this is what we get, 2 in the numerator and 2 in the denominator cancel each other, you are left with this expression HII plus Hij divided by 1 plus Sij. And I hope it is not very difficult to understand that for E2 we will get more or less the same expression, except for the fact that instead of plus sign we are going to get minus sign. Okay? Please work it out yourself and satisfy yourself that that is the case. What is the next task at hand? We should try to evaluate HII and Hij. We should try to simplify their expressions in terms of some things that we know. So let us do that. To evaluate it, we will write down the expression for the Hamiltonian. Now when I do that, I can take these first two terms in bracket. Isn't it essentially a 1 electron Hamiltonian? So we are going to write it as H hat 1 electron. So now our Hamiltonian H hat is equal to a 1 electron Hamiltonian minus q e square by rj plus q e square by capital R, and remember, by Born-Oppenheimer approximation this last term is essentially a constant. Okay. So this is what it is. So HII is equal to integral phi 1 si H hat phi 1 si. We are going to put this expression for the Hamiltonian in the expression for HII, and obviously we will get 3 terms in that case. We will get a sum of 3 integrals. These are what they are. Let me just write it like this. We will need some space to write more things as well. HII turns out to be integral 1 si. Here instead of A and B I am just writing I and J, more general coefficient, more general notations. 1 si H hat 1 e 1 si. Now this is something nice. Remember this phi 1 s is a 1s orbital, and what is the 1 electron Hamiltonian? The 1s orbital is going to be an eigenfunction of 1 electron Hamiltonian. So energy of 1s orbital is actually going to come out. So this first one is very simple to work out. What about the second one? What about the third one? We will see. Even in the second one you can see that 1 by r is constant, so that can come out. Third one, well, that is more interesting. Okay. So this is how we write it now. First we take this constant out, it becomes q e square divided by r integral phi si phi si. Now we know that that is equal to 1. We are working with normalized s orbitals. That is great. Now what we do not know is the third one. First one I already said, I do not know why I have not written it yet, but it will come also. In the first one I think you can understand what will happen. Energy of 1s orbital is going to come out. Inside you are going to be left with integral 1s and 1s, which is going to be 1, and so this will simply become, the first term will simply become energy of a 1s orbital. Second term is q square multiplied by, well, capital S. No, just q square by capital R, no capital S. Third term is minus q square multiplied by phi 1s I, phi 1s j divided by rj. What is this? This is called an integral j The name is Coulomb integral. When you say Coulomb, what do you think? Which field of physics would you think of if I took the name of Coulomb? Electrostatics, right. So, this Coulomb integral has got to do with electrostatics as well. See, what do I have in the numerator? I have 1s square, phi 1s square. What is phi 1s square? Remember, that is the energy density, right. So, inside the integral I essentially have phi 1s square, I will write I also, and here it is Rj. So, if I draw it like this is the 1s orbital I am talking about, if this is I, and the distance I am talking about is this Rj, right. So, what is this? If I just multiply it by electronic charge, that gives me charge of this electron cloud. Okay. This square is essentially your probability density. Probability density multiplied by charge gives you charge density. So, in the numerator, if you just multiply by E, which is just a constant, that is a measure of, that is your charge density. So, we have a charge density at a separation of Rj from the second nucleus. So, this essentially then gives me, well, one term gives me for a particular value of Rj the potential for electrostatic attraction between the second nucleus and the electron cloud around the first nucleus. Okay. Similar treatment is encountered if you want to talk about, say, electrolyte solutions. In electrolyte solutions, what we do is we take, say, a positive ion, cation, and we take the ionic atmosphere to be a delocalized negative charge to keep charge balance. So, similar treatment is there as well. You consider the electrostatic attraction between this point positive charge and this negatively charged cloud, ionic atmosphere. Same thing here, and you are integrating over all space. So, that will give you the total potential energy for electrostatic attraction between one nucleus and the electron charge cloud, on the near the other nucleus, alright. So, it has a physical meaning. J Coulomb integral talks about an electrostatic interaction. Okay. So, let us write the expression for HII now. The first term is E1s as we said, second term is Q square by capital R, third term is minus Q square J. Okay. Very nice, we got HII already. Why do we want HII? Because HII appears in the expression for energies E1 and E2. What is the next integral? Hij. Hij is a little more interesting. Why? Because unlike HII, you have one s orbital in the bra vector, a different s orbital in the ket vector, and you might as well start guessing which quantity, which integral we are going to encounter in a similar like that, in a situation like this. So, this is your Hij. Again, the first one there is no problem, we still get energy of 1s orbital. Second one, once again your 1 by r is a constant, it comes out, but when 1 by r goes out, what do you have inside the integral? Integral phi 1s I, phi 1s j. I hope by now we all recognize this integral. This integral is simply the overlap integral, Sij as we are putting it here, more often we just call it capital S. So, what is Hij? First term we have no problem, I do not know why I have written it in so many steps. Anyway, second term is Q square by capital R, integral phi Si, phi Sj, third term is this integral which looks somewhat similar to the Coulomb integral, but not exactly the same. We have one s orbital in the bra vector, we have another s orbital in the ket vector. Remember here Rj is not a constant. Okay. So, how you evaluate these integrals, we will come to that. Okay, but let us write this expression. The first one, what happens is you take the energy of 1s orbital out, no problem with that, but inside you are going to have integral phi 1s I, phi 1s j, that is again your overlap integral. So, first one will be energy of 1s orbital multiplied by overlap integral, that is the difference between Hii and Hij. Second one also is Q square by capital R multiplied by S, overlap integral shows up in Hij, it did not show up in Hii or Hij. Now in the third term again we have an integral which at the moment we do not know what to do with. We will give it a name. It is, since the earlier integral was called j, we go alphabetically and we call this one capital K. Integral phi si phi sj capital phi si phi sj divided by rj. And there are textbooks in which they try to make sense of it, but I do not think it is a good idea. This is a purely quantum mechanical quantity. It is called an exchange integral or resonance integral. So, this is what your expression is. It is very important to understand this is a purely quantum mechanical concept, there is no classical analog. So, to say that when this electron is here, that charge cloud interacting with the other nucleus, and then when they change places that gives extra energy, all this is trying to extrapolate the classical logic too much into the quantum world. You cannot do it beyond an extent. So, please understand that it is a purely quantum mechanical concept. Nobody knows, to be honest, any classical analog for this. So, let us not even try. Okay. So, we have the expression for Hij, we have the expression for Hii. What will I do? I will now just put the expressions in the expressions for E1 and E2, and here I am going to go fast because it is so easy. I will just put everything in. If you want, you please pause and do it yourself. Please do it yourself, then you will understand. This is the expression for E1, this is the expression for E2. Now, look at the expression. What do we get? E1s is the energy of an isolated 1s orbital. What is Q square by capital R? You see this plus Q square by capital R appears in both E1 and E2. So, that is essentially the internuclear repulsion between A and B. So, no matter what you do, that internuclear repulsion term will be there, and depending on capital R it will be large or small. If it is very far away, capital R is large, this second term will be close to 0. If it is very close to each other, it will be very large, but it is going to increase. So, if I just consider the two terms, the first two terms, then I can draw like this. This here is the energy of the 1s orbitals. Both of these energies would increase to some value, and this is going to be how much? This difference will be Q square divided by capital R. As you understand that this extent of destabilization is going to change depending on what is the value of capital R. Now, we have something interesting. The third term has a negative sign in both the cases, but here in the numerator we have j plus k, and in the denominator also we have 1 plus s. Here in the numerator we have j minus k, and in the denominator we have 1 minus s. Now, j, k, s, these are integrals. We have already shown how s varies, and s is definitely something that depends strongly on capital R. J and k can be evaluated not analytically but numerically, meaning for different values of capital R you can just put in all the values, and by brute force you can calculate what will be what will that integral be by doing summation. It is not very difficult to do if you know a little bit of computer programming. Okay. This is where computer programming comes in big time in chemistry, alright. So, this is what you get. For E plus or E1 you have a function that goes through a minimum. This is the energy, remember, of the bonding orbital, and here this is the energy of the anti-bonding orbital, which increases monotonically when you decrease capital R from infinity to very small values. This position or internuclear distance where you get an energy minimum for E1, that is the internuclear bond distance, and you can look at these insets. So, here this is a situation where the two nuclei are very far apart from each other. See what the energy is, and you can work out what S is. When they are at internuclear separation, this is what the wave function would look like. There is strong reinforcement, okay. And in case of the minus combination of the orbitals, this is a situation when they are very far away, it is still 0. When they are very close, say when they are at this equilibrium bond length, now you have this destructive interference between the two wave functions, and energy goes up to this value. And another point to note is that at equilibrium bond length, stabilization of the bonding orbital is actually less in magnitude compared to the destabilization of the anti-bonding orbital. You can explain this qualitatively by talking about build up of electron density and depletion of electron density between the two nuclei, but only qualitatively. Alright. So, these are the energies of H2 plus. Now, the way we proceed now is that we can just fill in electrons if you have more electrons here. That is how you handle H2 and other diatomic molecules, homonuclear diatomic molecules. But before that, this is an executive summary of what we have learned so far. And another thing that I want to say here is that this is what happens when you talk about hydrogen. If you want to talk about homonuclear diatomics like C2, N2, O2 and so on and so forth, you might need to, you will need to invoke the combination of not only 1s orbitals, but also 2s orbitals, 2p orbitals and so on and so forth. You can do it in exactly the same way, and you can generate orbitals bonding and anti-bonding in this way. Okay. So, I am going very quickly through this because it is not all that difficult for you to figure out. One thing that I would like to point out is that symmetry of these orbitals is actually they have a role to play later on in many different things. So, let us note the symmetry, and let us note the symmetry using these linear combination of p orbitals. When there is pi bonding, side on overlap, this is the kind of contour diagram that you generate. See, here we have plus sign and here we have minus sign, right, sign of wave function, I will just write beside it plus and minus, and here you have a node. So, if you start from any point of the wave function, go through the center, equal distance on the other side, you get a change in the sign of the wave function, right. So, this is called antisymmetric with respect to inversion, and the term for it is ungerade. So, these orbitals, these molecular orbitals come with the subscript u. So, this is called pi u orbital. You can neglect this one for now. Why pi? Because it is a pi interaction. If I go back to the orbitals that we have drawn, molecular orbitals, what does this orbital look like when we combine this 1s and 1s? For the bonding situation, it is like something like this. The contour diagram would be something like this. Now see, it is plus everywhere, right. So, if you go from any point through the center, equal distance to the other side, you get no inversion at all, no change in sign of wave function. So, this is called a sigma g wave function, G for Gerade. Gerade and ungerade are German words. Well, Gerade means symmetric, ungerade means symmetric as far as we are concerned. Now, what about the anti-bonding orbital for the H2 plus? There we take something like this. You have depletion. So, you have a node in between, right, this is the node. So, here the wave function is plus, here it is minus. Start from any point, go through the center, equal distance on the other side, you have inversion. So, this is called sigma u. Well, for now let us say that this is sigma because it is sigma interaction, and this one here is pi because you have pi interaction. There is more to it, it comes from the symmetry notations, we will not get into that in this course. But this is what we get for sigma interaction involving s orbitals. This is what we get for pi interaction involving p orbitals. So, the bonding orbital here, so for sigma interaction involving 1s orbitals, the bonding orbital has Gerade symmetry, the anti-bonding orbital has ungerade symmetry. For pi bonding with p orbitals, the bonding orbital actually is ungerade, and anti-bonding orbital you see this is plus, this is minus, this is plus, this is minus. So, anti-bonding orbital is actually Gerade, pi g. And another thing that we often do is that for anti-bonding orbitals we put star. Okay. Different books use different notations, but this is the notation that is used most universally, star for antibonding and Gerardet and Ungerardet to indicate whether they are symmetric or antisymmetric with respect to inversion, right. So, this is in a nutshell the symmetry of orbitals that we just discussed. You can have different kinds of bonds, sigma, pi and delta. Sigma is head on, pi is with p orbitals, this is pi, with d orbitals this is pi. No, with d orbitals this is pi. Of course, I do not have enough fingers to show you the 2 lobes at the bottom as well for d orbitals. These are the 2 lobes at the top. This interaction is p interaction. So, once again s orbitals sigma interaction, no pi interaction possible. P orbitals sigma interaction, pi interaction. D orbitals, well, you can have sigma interaction also, right. D orbitals you can have this kind of sigma interaction, or maybe I should show this kind of sigma interaction. Where is pi interaction? Like this, and this is delta interaction, face on, head on, side on, face on. So, these are the different kinds of bonds. We will not discuss the symmetries of orbitals and all these in this course, but it is a good exercise for the students to work out by themselves. Now, what we have done so far is that we have generated the alphabet by which we can discuss homonuclear diatomics in terms of molecular orbital theory. We have generated the molecular orbitals using the single electron, 1 electron molecule, that is H2 plus. Next, we are going to learn how we can fill in electrons into these same orbitals and how we can develop a molecular orbital theory of dihydrogen.